Hello everyone. So today I'll be performing an experiment which is based on Hilbert transform, and we'll try to see how we can apply Hilbert transform to look at various aspects of the signal. For example, we can look at the decaying part of an exponentially dying sinusoid. We can look at whether we can detect peaks in a signal or not. So, and also we can go through different aspects. I'll explain all of them one by one. Right. Okay, so this is my first code which is going to show us about how we can whether we can see the Hilbert transform. Okay, so let me explain this part of the experiment. In what we have done is given an input signal whose frequency is varied with time. As you can see, it keeps increasing, and when we are trying to see instantaneous frequency of the signal and see whether the changes are following up or not. As you can see in the graph, initially the frequency is quite low as expected. When it keeps increasing, however, you see the rise in the frequencies are steep, and there are certain overshoots that are happening. Well, these overshoots happen due to some computational errors and the fact that the frequency changes in our signal are not continuous. Okay, we are going to we now move on to the next part of application of Hilbert transform. So in this part of signal, what I have done is that there is an exponentially decaying signal, and our aim in this part of the experiment is to determine this coefficient through Hilbert transform. I mean, that is to determine the decay rate of this signal. Okay, so that is done by calculating instantaneous amplitude of the Hilbert transform that is obtained on after sending it as an input to the Hilbert function. The amplitude will basically give the exponentially decaying part, and applying logarithm to it divided by the entire time, you can obtain the decay rate. Of course, this decay rate, as you shall see, will vary a little bit here and there, so we need to actually calculate the mean of this value. Now, for simplicity, I have not plotted the entire decay values, and I have truncated some values because of the fact that due to some computation errors, there are some abnormalities that you will be observing in the graph. Okay, so let me run the code. Okay, so let me show you. So you can see this was my exponentially decaying sinusoid which I have given as input. Through Hilbert transform and applying an amplitude or absolute function in the MATLAB, I am able to obtain the amplitude curve which basically tracks down the instantaneous amplitude. Now, applying logarithm and dividing by the time, we are going to get the instantaneous decay value. As I said earlier, due to some computation errors, the decay rate initially is very large negative value, and as the signal moves forward, we calculate the value. As you can see, there are certain overshoots and some peaks and troughs in this graph, which indicate that this is not the the calculation of instantaneous decay requires certain more robust methods. Now you can see that this curve on an average is around minus 2.0, which is expected as we had given our exponential decay rate here as minus 2. Right? Now let's move to the next part of the experiment. So in this part of the experiment, I'll try to show that a peak in a signal can be detected using Hilbert transform and taking the imaginary part of the Hilbert transform. So this is implemented as this way: Zx, which is the Hilbert transform of the x, while x is an signal that I have generated, which is nothing but 1 by 1 plus t square. After applying Hilbert transform, I have taken its imaginary part, and then we are going to see where this imaginary part of the Hilbert transform crosses 0. So this part of the code, detect x, this thing is nothing but simply zero crossing detector. So once the zero crossing is detected, we are going to spike, or we are going to create a value 1 over there. So in output graph you shall see a spike wherever there is a 0 crossing. Okay, right? So let's observe this outputs. Okay, so you see this orange colored signal is my original input signal, which is 1 by 1 plus t square. The blue colored one is the Hilbert transform and its imaginary part. As you can see, the blue colored one, which is basically the 0 crossing detector's output, is showing a peak at exactly when the Hilbert transform's imaginary part crosses 0, and you can see that at this value we also have a peak of the signal, right? So we can extend this concept so that we can detect multiple pulses or multiple peaks inside the signal. As this will be my next part of the experiment, I'll show you. Okay, so what I've done, using simple pulse gen function, I'm able to generate pulses, which is nothing but simply t minus a whole square into t minus c whole square, where a and c represents the end points of the pulse. Now have squared them because they provide some kind of smoothing effect or in the derivative. Otherwise the pulses will have discontinuities in its slope, and so will cause spikes in our Hilbert transform, right? To avoid such things, I have squared them and control their amplitude by estimating their amplitudes at the peak values and dividing them by that value. So if you estimate exactly, so we are going to get this output. Okay, now having generated one pulse, I am going to repeat this over the entire range. So as you can see, pulse gen 0.5 to 0.7 is going to create pulse starting from 0.5 time and ending on 0.7 time with an amplitude of unity. 4 star will generate a pulse with a amplitude of 4 with 1.5 1.7 as the time limits. This and so and so. So let's run the code and see if we are able to detect multiple pulses. Okay, so the orange colored signal is the pulse signal or the signal containing multiple peaks. As you can see, I have created various and different types of peaks with varying variance and peak amplitudes. So you can see that Hilbert transform, wherever it's crossing 0, the zero crossing detector is able to create a spike and thereby indicating the presence of a peak in the signal. However, at the end part you can see that there is a slight shift. Now this is the problem with Hilbert transform. When two peaks come really close by and one of the peak is very large, the peak with smaller amplitude does not get detected. As I shall show this in the next part of my experiment. Okay, so this is the same code as this one, except that the pulse locations have been changed, as you can see here, where it is 0.8, 1.6, while these locations are different, right? So let's run this code and see. Yes, so you can see that when a bigger pulse is brought very close to a smaller pulse, the smaller pulse goes undetected as the bigger one dominates it. So you can see that the Hilbert transform has, although this kind of shape exists, which should have been quite close to 0 for detection, but because of this bigger pulse, it has got suppressed or in amplitude or gone below 0 value. As a result, 0 crossing detection method does not work, although it quite accurately determines the position of peak for bigger pulse, but for rest other pulse the position get a little bit distorted, as you can see for both of the cases here. So we come to the end of our experiment. Hope you enjoyed our video.